Hey folks, welcome back. Today we're going to continue talking about power series and applying this central theorem which we saw last time. So the power series, you can see, is defined here. The general power series has a center at the point C. The a sub n are the terms. The first term is going to be a sub 0, and then the next one's a sub 1, x minus c to the power of 1, and then a sub 2, x minus c squared, and so on. So there's the general form of a power series, and we saw them last time. And the key result of this theorem is that every power series converges on an interval around the center. Now that interval might be infinitely big if the radius of convergence is infinity, but essentially what we're going to do is we're going to start at the center and we're going to see convergence, a distance r to the left and the right. So this is the point C plus r, this is the point C minus r, and every power series has this property that it converges within a radius of a radius of r of this central point C. And the central point we can just read off. So this is a common feature of all power series convergence. The radius of convergence might be 0. Remember we talked about that. That means it just converges right at the center. Or the radius of convergence might be infinity, which means it converges for all values of x. So you can go infinitely far in both directions from the point C. Or more often, there's some specific radius, finite number r, that's bigger than 0. So today I just want to build on what we did last time and think about the radius and the interval of convergence. Remember, the interval is literally, in this case, it would be that interval from C minus R to C plus R. And as we talked about last time, we have to explicitly look at those points on the edges to see if it converges or not there. That's often the case. But to start with, let's build a power series that has the form x to the n over n factorial. So x to the n over, make that an n, x to the n over n factorial. So if we write that out, we get a power series, and remembering that 0 factorial and 1 factorial are both 1, we get these terms, then x squared over 2 factorial and x cubed over 3 factorial. And remember, a 3 factorial is just the product of 1, 2, and 3. N factorial is just the product of 1, 2, 3, all the way up to n. So we want to find the radius of convergence and the interval of convergence for this power series. The natural way to approach this one is to use the ratio test. So let's do that. So we're going to take the limit as n tends to infinity of these consecutive terms. So remember, it's a sub n plus 1. Looking back here, this is our nth term. And I haven't said it, but what's the center of this series? Well, the center here is 0. Because I've put c equal to 0 there. But the nth term is everything in that yellow box, and so we're going to take a sub n plus 1, which is in this case, the minus 1 to the n and the n factorial piece. And then we've got the power of x as well, and we're going to divide it by the corresponding nth term. And so just writing that out, and again using the idea that this is our n plus 1th term, and this is 1 over the nth term. So I'm just taking the reciprocal here. So this is a sub n, it's all of this, but the reciprocal of it. So we need to take that limit, and taking that limit, there's going to be a lot of cancellation. What I'm going to do is notice that the minus 1 to the power of n plus 1, the minus 1 to the power of n, so that leaves a single minus 1. The absolute value is going to get rid of that anyway. And then we can cancel the x to the n here with the x to the n there, and that's going to leave an x in the numerator, and then I'm just going to leave everything else there, and I'm going to put these factorials together. And remember, n factorial is all of the numbers up to n multiplied together, whereas n plus 1 factorial is all of the numbers up to n plus 1 multiplied together. So we end up with that. And again, we see ones like this. We get the cancellation of those terms, we get the cancellation of those terms, we're left with n in the denominator, right? So what we're left with here is the limit as n goes to infinity. The absolute value is going to get rid of the negative sign, so we're going to just end up with x over n plus 1. Now, x is a fixed number. We want to find out what values of x we converge for here, but if we take this limit as n goes to infinity, we're going to get 0, because the n is in the denominator there. So that's 0. And that's less than 1 for any value of x, right? It doesn't matter what value of x I give you, as long as it's a real number. So for all real numbers x, this is less than 1. And so by the ratio test, this series converges for any value of x. right? Because the condition in the ratio test is that this limit is less than 1. And this limit is always 0. For any value of x, it's 0. So the radius of convergence is infinity. I can go infinitely far to the left and to the right of the origin, which is our center, and the function will still converge. This power series, if you think about it as capital F of x, that function f will still converge. And so if the radius of convergence is infinity, then the interval of convergence is all the real numbers. So from minus infinity to infinity. So this power series defines a function for every value of x, which is different from the other ones we've seen that only defined a function on some smaller region where they actually converge and then they diverged everywhere outside that. Let's do another. For this power series, again, we can write it out. We start when n equals 1, so the first term is just x to the 1 over 1 to the 1, so that's just x. The next term is x squared over 2 squared, the next one's x cubed over 3 cubed, the next one's x to the 4 over 4 cubed, 4 to the 4, and so on. So I got a nice power series there. We want to know, again, what's its radius of convergence and what's its interval of convergence. So we can sit down and we can use the ratio test on this one, or we could use the root test, because notice that the nth term here can be written as just a power of n. And so you applying the root test, well, remember we take the nth root of the absolute value of the nth term, which is x to the n over n to the n. And if you think about that root as we can put these inside the absolute value. If you think about that as an nth power, and then the root is a 1 over nth power, these two multiply and give you n over n, which is 1, so this just leaves the absolute value of x over n. And then the root test tells you to look at the limit of that as n tends to infinity. So the limit as n tends to infinity of the absolute value of the nth term. Remember, we write that as, sorry, I put the n in the wrong place here. This is a sub n x to the n. The absolute value of that, the nth root of it, what we end up with is what we just calculated, which was the absolute value of x over n. And in the limit, that's 0, and that's less than 1. And so just like the ratio test, the root test says as long as this limit is less than 1, the series converges. And so we have the same conclusions we had last time. The series converges for all x because it doesn't matter what value of x I'm using here, as long as the x is finite, right? As long as the x is a real number between minus infinity to infinity, the limit as n goes to infinity is going to make this denominator bigger and bigger, and so this limit's going to be 0. And so that means by the root test, we've got a convergent power series here. Again, the radius of convergence is infinity, and the interval of convergence is all the real numbers, minus infinity to infinity. And again, I didn't mention it, but the center of this series, it's not so relevant here, but the center of this series is again c equals 0. So hopefully this gives you an idea. Again, I'm looking at these and I'm thinking, what approach do I use to solve the problem? I'm looking at this and I'm seeing lots of powers, and so if you see lots of powers, if everything's raised to the nth power, then the root test is really the way to go. But if there's a mix of things, some of them are raised to powers, some of them are factorial, some of them are polynomials, then use the ratio test. Let's do one more. So this one's a bit more complicated looking, and again we can start writing out the terms. Notice the power up here is always even. 2n is going to give you an even number every time. So when n is equal to 0, that produces something to the 0, which is 1. This is 1. So the first term is indeed 1. The next one is going to be 2x plus 3. Now it's going to be n is 1, so that's going to be a squared divided by n is, what did I say? N was 1. So this is 4 times 5, which is 20. And the next one's going to be 2x plus 3 to the power of 4, all divided by 5 squared times 3 squared. And then the next term and so on. It's just worth writing these out sometimes because it gives you a feel for the terms and what it looks like. What's the center here? Well, the center is where this term is equal to 0. Right? The center is the value of x that will make that 0. Because going back to the beginning and looking at this, the value of x that I would plug in there to make that term 0 would be c, right? Because then you get c minus c to the power of n, which is 0 to the power of n. So the center is literally the point that makes that term 0. So in our case, the center is where all of that stuff, 2x plus 3, is equal to 0, right? Which means, solving that, it means x is equal to minus 3 halves. Because I could rearrange that, right? Because I could write 2x plus 3 to the power of 2n. I could factor out that 2, right? I could write it as 2 times x plus 3 halves. And now this is raised to the power of 2n. And so this is rewritten as 2 to the power of 2n, x plus 3 halves to the power of 2n. And so that whole series could be rewritten like this. See, I've substituted that in. And you can explicitly see there what the c value is. Right? There's the c value. I've written x minus negative 3 halves instead of x plus 3 halves. And what was 2 to the power of 2n, well, that's 2 squared, which is 4 to the power of n. So there's the 4 to the power of n. So these two series are the same. And looking at this second one, you can read off the center, right? The center is clear. The center is where x is equal to minus 3 over 2. So we'll call that c. But that's what I found up here, just by taking that term and setting it to 0. There's no particular value in writing it this way right now, but you can see sort of the comparison maybe between writing it this way and writing it that way. All right, so let's take this and just looking at these terms, there's exponential terms. So we've got these terms that are exponential. We've got this term, which is a polynomial. We're going to need to use the ratio test on this. So let's do it. So if this is our series, our general term in the power series is always a sub n x minus c to the power of, that's meant to be an n, even though it looks like a 2. And so let's do the ratio test, which involves taking the limit of the n plus 1th term divided by the nth term. And in this case, that involves the center. So it's a bit more complicated than I wrote it down last time. But we can fill this in. This is going to be 2x plus 3. Now it's going to be raised to 2 lots to the power of n plus 1, because I replaced n with n plus 1. And then it's 5 to the power of n plus 1. And then it's n plus 1, all squared. And then that's multiplied by, I'm just going to write the reciprocal of the nth term. So I'm just going to flip that nth term and write it down as it is above. So this is to the power of 2n. And now we do the cancellation. Right? The ratio test always works in the same general way. I'm going to cancel a bunch of stuff here, so we're going to still be left with the limit. But when we do the cancellation, you can see that I've got, this is 2n plus 2. And I've got 2n down there, so all of that is going to cancel with the 2n, and it's going to leave 2 of them. So we're going to have 2x plus 3 all squared, because there's still 2 left. With the 5s, you can see here with the 5s, I've got a 5 to the n on top, I've got 5 to the n plus 1 on the bottom, so I'm going to cancel the 5 to the n's here, and that's going to leave just 5 to the power of 1 in the denominator. And then separately, I'm going to write these n terms. This is n plus 1 over n plus 2, all squared. And then we need to take that limit, but that's the kind of limit we've dealt with before, right? The limit of a polynomial. You hopefully are getting used to this at this point. In the ratio test, that limit of a polynomial doesn't really contribute, because I can divide top and bottom here by 1 over n. And so just like every time we see a polynomial in the ratio test, this ratio is going to be 1. The limit of the polynomial is always going to give 1. So this is the limit as n tends to infinity. Taking this piece of the limit, we find 1, and then that leaves us the rest. It's the limit as n goes to infinity of 2x plus 3, all divided by 5. This is squared. There are no n's in there at all, so the limit is just, well, 2x plus 3, all squared, divided by 5. And for that to be less than 1 is what we want for convergence, right? So for convergence, we need that limit to be less than 1. And I drop the absolute values because, well, this is the square of something, and the square of something is always positive, and this is just 5, and that's always positive. So this whole term is still positive. I don't need to write the absolute values. So there you go. There's my condition for convergence. Let's have a look what that means. So we took the limit that the ratio test tells us to think about, and we found this quantity, and it has to be less than 1. Well, I can rearrange that, right? It has to be less than 1 if I want convergence. So I want this squared to be less than 5. And that means that the absolute value of 2x plus 3 has to be less than the square root of 5. Put another way, that means 2x plus 3 has to be between minus the square root of 5 and positive the square root of 5. Right? So you can see that the square root of 5 here is our radius of convergence. And the absolute values appear here because I'm squaring something and I'm getting 5, and so I don't know whether that something was positive or negative, so it could have been either, which is where the absolute values are coming from. And we can rearrange this inequality. We can pull out the 2, just like I did on the previous page, right? We're going to see the center. We can't avoid seeing the center because that is involved in the radius of convergence. So what we end up with is the condition, if I just divide that 2 out, right? Technically, this is the same as the absolute value of 2 times the absolute value of x plus 3 over 2, and that's less than square root of 5. Absolute value of 2 is just 2, and so I can divide it on the other side. There we go. There is our statement for convergence. That's where this series converges. As long as x is in that region, the series will converge. In other words, as long as x satisfies that inequality, the series will converge. Well, let's think about what that inequality means. Let's draw the x-axis. Looking at that inequality, the center here is minus 3 over 2. What this literally means, if you think back to your pre-calc days, this quantity measures the distance from the center. So that absolute value is measuring the distance from the point minus 3 over 2. So in this case, we're saying it's less than root 5 over 2. So the end of this interval over here is minus 3 over 2 plus root 5 over 2. And then we go to minus 3 over 2 minus root 5 over 2. So our radius of convergence here is the square root of 5 over 2, right? Because we're moving square root of 5 over 2 in each direction from the center. This is always true. The quantity, the absolute value of x minus c, that's always the distance between x and c. So if I put that into an inequality, I'm saying I want the distance of x between x and c. Between is what I meant there. This is the distance between x and c. And so in this case, the distance between x and minus 3 over 2 has to be less than the square root of 5. So that inequality is satisfied for any x that's less than the square root of 5 away from the center. So there's our center, and there's the center plus the radius of convergence, and there's the center minus the radius of convergence. I know it converges everywhere inside that region by the ratio test. I've still got to look at the edge points, right? I've got to look at the points here. The square root of 5 over 2 minus 3 over 2, and minus 3 over 2 minus the square root of 5 over 2. So let's look at those 2 points. So on the right boundary, where x is minus 3 over 2, the center, plus r, which is root 5 over 2, let's quickly just calculate what 2x plus 3 is, because that's where x appears here. So 2x plus 3 is going to be, well, 2x is minus 3 plus the square root of 5, just doubling all of that, and then I'm going to add 3, so that's the square root of 5. Right? So when I plug that in here, what we're going to get is the sum of the square root of 5 to the power of 2n divided by the rest of it, 5 to the n plus 1 all squared. And so this is going to be the sum, again, square root of 5 squared is 5. So this is 5 to the n over 5 to the n. So they cancel, and we're just left with this. So n equals, I think, no, we started at 0, n equals 0 to infinity. There we go. So at this boundary, what we have is something that looks very much like p-series with p equals 2. We could use the limit comparison or the direct comparison test to compare this series with 1 over n squared, because we literally know that that is equal to, well, that's going to behave in the same way. Let's use the direct comparison test because I think it's easier here. So I'm going to think about the term, the series we're interested in is this one, n plus 1 all squared. And then the other series where we've got is, in this case, just 1 over n squared. So we know that the sum of the b's, so the sum of 1 over n squared, n equals 1 to infinity, converges, get that right, it converges since it's a p-series with p equals 2, and that's bigger than 1, right? And so we know that converges. Notice that n squared is smaller than n plus 1 squared, right? This is true for all n. And so we can rearrange this, divide the n plus 1, it's a positive number, it doesn't change the inequality, onto the left, and divide the n squared onto the right. And so we see that 1 over n squared is smaller than 1 over n squared for all n, right? In particular for all n greater than or equal to, well, 0, let's say. And then that's what we needed. Because when we add these terms up, we're adding up a bunch of numbers that are smaller than what we get when we add up this series, but we know this series converges. So by the direct comparison test, we've shown that this series converges. I said it, but I didn't explicitly write it down, but both of these are positive. We need that for the direct comparison test to be useful. But we know the A sub n's and the B sub n's are positive. We know that this is a convergent P series, because P is 2, and that's bigger than 1. And we've got this inequality. And that's the information we need to apply the direct comparison test, so we know our series converges at that point. Let's look at the other end, because we just did the point here, and we found it converged, so convergence is included on the right. Let's look at the left. On the left, when we calculate 2x plus 3, we're going to get minus 3 minus the square root of 5 again, and then we're going to add 3. So that's our 2x, right? And then the 3's cancel, and we're left with minus the square root of 5. So when we plug that result in to find out what the series looks like, we end up with this whole thing being minus the square root of 5, and minus the square root of 5 to the power of 2n, divided by 5 to the n, and n plus 1 all squared. And that's going to be, well, this is 5 to the power of n divided by 5 to the power of n again. We're squaring it, so the negative sign goes away. Right? So the only difference here from the previous case was that negative sign. When I square it, that's gone. And so we end up with exactly the same series that we saw last time. The limit, the sum from 0 to infinity of 1 over n plus 1 all squared. And we literally just showed that that was convergent. It was exactly the same series we looked at in the previous endpoint. And so what does that mean for the overall series? That tells us that this series converges in that interval and at both ends. So going back to our picture before, we have shown that it converged at the left and the right side. So it's convergent at the endpoints, and it's convergent in the middle. And so this inequality here is essentially describing the convergence with an equal sign. So it converges for all x that satisfy that inequality. In other words, the center here is minus 3 over 2. The radius of convergence, which we found before, we knew that from the ratio test, is the square root of 5 over 2. The interval of convergence is all the values of x that are greater than or equal to minus 3 over 2 minus the square root of 5 over 2, and that are less than or equal to that. In other words, this inequality is describing the interval of convergence because it's saying precisely what I just said. And that's the interval of convergence written in inequality form, and here it is written in our sort of interval notation. Okay, well, that's quite a complicated problem, right? All of the pieces came together in that problem. We saw how we're using the ratio test and the root test, maybe sometimes, but the comparison test or the limit comparison test, it's worth noting that I could have used the limit comparison test here because I'd be comparing with this same one and I'd look at the limit of these terms to those terms. We've seen how all the pieces fit together. Next time, we're going to talk about how we can use these power series to represent special kinds of functions. And then after that, we'll talk about how we can represent any kind of function in the next section. So thanks for tuning in. See you soon.